Good morning. I'm Professor T.S. Kalkur from the Department of Electrical and Computer Engineering, University of Colorado at Colorado Springs. I'm going to give one hour presentation on microelectronic circuit design, and I've given my email address tkalkur@ccs.edu, and I'm at Colorado Springs, a beautiful place with lots of mountains around and 6,000 feet above the sea level. We are at mountain time now, 9 p.m. So my presentation outline is I will briefly give my self-introduction and importance of microelectronic circuit design, what kind of expectations of academic knowledge in that area, requirements for microelectronic curriculum, typical, and then finally the summary. As self-introduction, I'm a professor and department chair at the Electrical and Computer Engineering at the University of Colorado at Colorado Springs. I teach courses in CMOS circuit design, analog IC design, RF CMOS circuit design, mixed signal design, electromagnetic effects in integrated circuits, RF circuit design, and physics of semiconductor devices. My research area is microelectronic circuit design and fabrication. I work in the area of tunable devices for wireless applications, novel materials and devices for circuit applications. I have published over 20 papers in journals and conferences with 4 patents. I graduated over 16 PhDs and about 80 master's students, all employed. And in my sabbatical, I worked in HP Lab, Palo Alto, Atmel Corporation, Test Semiconductor. I regularly consult with numerous local industries, and I worked in ITI Bangalore for 4 years before I left India in 1981. So why microcircuit design is important? Because you know that electronics is everywhere. You take an electric car, and this electric car has typically about $5,000 worth of electronic components. If the car's cost is about $20,000, it has so many sensors, so many electronic modules, and so on. And it has low power electronics, high power electronics, all kinds of electronics. Or you take the PCs, and PCs have lots of electronics in them. Or you can take a solar panel. It has a solar panel, solar cells, basically semiconductor electronics, and then variety of power circuits. Or you can take an example of iPhone, and iPhone also has lots of electronics. So therefore, we motivate students. Electronics is extremely important, and especially how we design those circuits and things like that. So if you take a motherboard in a printed circuit board or any motherboard in any application, you see variety of integrated circuits there. You can see here, this motherboard has a Samsung application processor, and it has double data rate, SDRAM. It has an accelerometer. It is basically a microelectromechanical device. And then we have an Infineon smart power management integrated circuits. And it has a Skyverse power amplifier, and then so many power amplifiers, and digital baseband processor, power management chip, battery charger, then audio codec, touchscreen controller, display interface, and 1 megabit serial flash. So you can see the amount of circuit design knowledge the student needs nowadays is enormous. Because of a variety of chips, and then our problem is how to give this kind of knowledge for students when they graduate, because we don't know what kind of area they are going to work on. So chips needed in a motherboard. So basically we have processors, we have power management chips, we have memories, DRAM, SRAM, flash, we have analog chips, we have wireless communication chips, touchscreen controllers, battery chargers. So many low power and high power semiconductor microelectronic chips are present. So next is this is basically a ITRS roadmap for semiconductors. You see year and then 2011, 2015, 2019, 2023, how the device size is going on shrinking from year to year. If you take the first one, the flash, the 0.5 pitch in nanometers. So pitch corresponds to the length of the width of the line and the spacing, and half the pitch is basically correspond to width or spacing. It is about 28 nanometer in 2011, and 2015 is 18 nanometer, and 2019 is 11 nanometers, and in 2023 it is 7 nanometers. So it is international roadmap for semiconductors, like how the technology can change in the future. If you take in the case of DRAM, again there is a continuous downscaling of device dimensions from nanometer, 40 nanometers to 10 nanometers. And then if you take the multiprocessing unit in the specific integrated circuit environment, the dimension may change from 38 nanometer to 8 nanometer. And similarly, the printed gate length on nanometer dimensions. We are already using nanotechnology in our microelectronic circuits. Or multiprocessing unit, physical gate length, that's basically the drawn gate length in a device, is also in terms of nanometers in dimensions. And ASIC, like low stand power or ASIC standby power, everywhere you can see the dimensions are going on decreasing year by year. The next thing is what kind of students, when they graduate from an academic institution, what kind of opportunity they can expect in their career, for their career. So the students may work as a device engineer, or they may work as a process engineer or process integration engineer, a design engineer, a test engineer, product engineer, yield enhancement engineer, failure analysis engineer, reliability engineer, or research and development engineer. So there are so many positions available in an industry, and our job is to produce a student who can fit any one of these jobs when they graduate from a school. So what kind of knowledge we have to train him so that he become a successful engineer. If I want to explain, device engineer means basically his job is to, when the wafer comes from a fab, he will characterize and then he will give the model parameters to designer. Process engineer will develop semiconductor process, and then he will also integrate various processes so that we can get a semiconductor circuit out of it. A design engineer, basically he will test the device, he will design the device. The job is to test the device in at different stages of packaging or fabrication and so on in a cost efficient way. And the job of product engineer is to get a feedback from the vendors, so that how the product is working, or if there is any problem, or if there is any problem, how to fix it and how to make changes for the next subsequent design and so on. Whereas the job of yield enhancement engineer is, yield is an important parameter in a semiconductor industry, because unless you have the right yield, you won't make any profit out of it. Engineering is always done with the intention of making profit. Nobody runs an industry to make loss. So therefore, if you have a product, it depends on the status of the product also, because if it's a memory general product, we need about 90% yield. So if you make some chip, it works at 40% yield. Instead of earning money, we lose money. So then we have to find out where the problems are and then come out with strategies to improve the yield. And sometimes when you fabricate a chip, it may not work at the right specification, or it may not work at all. The job of the failure analysis engineer is to identify problems and why it failed and all those things. So he should be familiar with a variety of analytical tools and instrumentation tools so that he can find the fault. And reliability is an extremely important parameter, because when you design a chip, it has to work in very severe conditions. It may have to work at minus 40 degrees centigrade, and it has to work at 80 degrees to 100 degrees centigrade. So then it should work in all conditions in a way. So therefore we have to assure a customer the reliability of the product. And then of course there is always research and development to be done so that we keep abreast with the technology. So even in case of a design engineer, what kind of jobs are available for a students when they graduate from a school? So they may work as a digital design engineer, or an analog design engineer, or RF design engineer, power management engineer, mixer signal design engineer, or test software development engineer. And these chip design groups also vary from company to company. Large companies may have design groups with 1,000 engineers, whereas there are small companies where a single person may have to do all these things. So basically, a detailed designer will design a chip basically using the electronic design automation tools. Analog design, he will design basically filters, comparators, amplifiers, op-amps, and things like that. And RF design engineer, he will design low noise amplifiers and power amplifiers, mixers, all the RF front end. And then power management is also becoming extremely important. People try their best to conserve power in a chip. So therefore, he should come with all kinds of strategies so that he can prolong the power or battery life in an electronic system. And then mixed signal design engineers, basically they will be very good at interfacing analog and digital chips performances in a given mixed signal environment. And the job of test development engineer is he has to develop software and conduct test operations. And testing is also extremely important. Sometimes, for example, if it takes about 1 second to test a chip, if the time increases 2 seconds, instead of making money, you may lose money when you develop a product. So next thing is, as an academic, I have to see how to motivate students in microelectronics. Microelectronics circuit design is one of the most important aspects of undergraduate and graduate curriculum, since most final product will be based on an integrated circuit. So therefore, what are the coursework needed to develop a well-rounded microelectronic designer? So whenever a student joins to an undergraduate curriculum program, they are not aware of impact of microchip in their products, because a lot of students don't know what a microchip is and what it does and so on. And that's why he is not motivated to learn those things. Like, I don't know, like in India, when I was a student, I just followed what my dad said and pursued that area, whereas here students have to be really motivated to pursue a given area of study, and if they're not motivated, they're not going to study about it. So therefore, whenever a student joins an electrical engineering program, the first course we ask them to take is robotics. So robotics is basically it's a what is it called, plug and play kind of a course where students, they use a variety of sensors, and they use a variety of mechanical devices and so on, and they also learn some programming techniques, and then they see how the robot moves and all those things, and they get excited. So our main thing is make something which works, and then create interest, so that students know the importance of hardware and software in a given system. So now, what are the topics or areas to be covered in a microelectronics design? There is again it is debatable. As I told you, sometimes some students, some people, employers may say that, oh, we need only design engineers, whereas some employers say we need only engineers with a device physics background or some processing background and so on. But always we are worried because when we train students, we don't want to train them in a very narrow area of expertise because the scope of their work may change in a given time. Usually we expect around 30 years is the lifetime of an engineer, and in 30 years their responsibility may change significantly. So we identified certain areas where they have to have good knowledge in terms of fundamentals in addition to professional knowledge. So first area is we expect the device physics, because device physics is extremely important, because initially I showed a map of international roadmap on semiconductors. There we define the feature dimensions, how it changes in the next 10 years, and this is closely related to the device physics. So students should know the basic aspects of device physics, various devices, how they work, and so on. So next thing is the processing technologies. What is happening is we have more and more fabless companies in the United States. When I joined Colorado Springs, University of Colorado in 1985, we had about 8 clean rooms, and now we are left with only 1 clean room, and most of the processing technology has been transferred to countries like China, Taiwan, and so on. So we have lots of fabless companies which develop, which basically design chips. Sorry. Okay, I'll go to. So therefore, we use processing technologies. We have to teach them processing technologies like how to, and the cost of the different process changes very significantly. Engineering is not just designing or making an optimum product. We have to keep the cost of the product also into consideration. So therefore, giving a knowledge of processing technology is also extremely important, and we should stress them that we have to select appropriate process which justifies the cost. And next thing is the analog circuit design. So as I told you, like we have a concept of system on a chip nowadays. So therefore, how to incorporate, we have to give them certain knowledge of analog circuits, especially like designing, op amps, comparators, bandgap reference, and so on. And then next thing is the basically digital design. Of course, digital design in this is mostly a tools-based class, but of course they should have the knowledge of different circuit architectures so that they have they can troubleshoot when the problem comes in the future. And nowadays, next is the RF circuit design. We know that most of the circuits have now wireless communication associated with it. So therefore, they should have some basic knowledge of RF circuits like matching issues, matching networks, impedance matching, and then issues with low noise amplifier, noise in semiconductor devices, designing circuits for low noise, those kinds of aspects. And next thing is, once the circuit is made, they should do the packaging. And when you do the packaging, and then you have to assemble them in a printed circuit board, so they should have the effect of electromagnetic effects. Like as the frequencies increases, we see more electromagnetic effects in the chips, and therefore students have the background in that area. And next thing is the power electronics. Power management becomes extremely important. Like if you take in a typical cell phone, we change the backlighting intensity depending on the ambient power. So students should have certain knowledge of implementing this in chip technology. So next we go to the device physics. So now Device physics is a most fundamental class of circuit design because and we have to introduce the following concept like semiconductors. What are semiconductors? What is conduction band? Where is valence band? Intrinsic permeable, band gap. Because when a microelectronic circuit designer designs a band gap reference, if it doesn't have any concept of band gap, it doesn't make any sense actually. Like for example, what is 1.2 volt or electron volt and so on. In addition to that, when we get when new semiconductor technology come into picture, like we will have silicon germanium heterostructure bipolar transistors, we have gallium nitride based devices, and we have gallium arsenide based devices. So they should know at least some aspects of semiconductor technology to appreciate and understand the working of those devices. So therefore, having a good background in semiconductor is extremely important. In addition to the electrical properties, they should have some knowledge about thermal conductivity and so on, because sometimes the effect, self-heating and all those things in devices play an important role in the performance of the device. So next topic, which we have to introduce is the operation principle of like PN junction. PN junction, it may look a very simple device, but if you take a semiconductor chip with a billion transistors and with a billion MOSFETs, we have at least 2 billion diodes associated with them. And so therefore, the student should have a good background in PN junctions, like its operation principle, reverse bias, forward bias, junction leakages. And then, because junction leakage is extremely important when somebody designs a DRAM, the junction leakage currents in the diodes play an important role in the refresh clock rate or the power dissipation. So therefore, having a basic knowledge of these leakage issues are extremely important. Then capacitances, because we use the diode not only as a unidirectional conductor device, we use them as a tuning device. Like applying voltage, you can change the capacitance of the device. So that is extremely important. So therefore, when you teach a diode, it is better to teach them in a semiconductor cross section so that they understand what are the different regions, what diode means, P, N, and how you take the contact, whereas these are all surface contacts are taken in the same level. So, and why you need N plus area, what is the difference between N plus, the doping density, the metal semiconductor contact, all those basic concepts can be covered in this topic. So next thing is the MOS transistors. MOS transistors are extremely important, and therefore it is good to give them a background in the on the MOS transistor theory. They should have a basic idea of MOS operation, current voltage characteristics, capacitance voltage characteristics, and then the parasitic capacitances, so that we can highlight them. What is the advantage of silicon on insulator compared to the traditional CMOS technology. Then the scaling is extremely important, because in companies we scale down the devices continuously, and when you scale down the devices, the characteristics of the device changes. Usually what people do is called shrinking the device dimensions. So for example, if you have a circuit design to work at 0.25 micron, then when the technology changes, we may want to implement the same design at a much shorter geometries. But if schematic may look same, but the device characteristic changes. So therefore, they should be aware of the effect of scaling on the MOSFET characteristics. And next thing is the second order effects, like channel length modulation, threshold voltage effects, leakage current, like subthreshold leakage, junction leakage, gate leakage. Because so far most of the in MOSFET technology, we assume the gate MOSFET is isolated from source or from the silicon. But actually nowadays the gate oxide is becoming so thin, it is of the order of few nanometers, and there is a lot of gate leakage current. And every technology has a curve called bathtub curve. So when you shrink the device dimensions, you may see some improvement. But if you try to do, we are human beings, try to become greedy and try to do more and more shrinkage, then you get a reverse effect. You may not get the right advantage, especially in this case, the leakage current, increasing leakage current. So it is better to cover all those basic aspects of scaling down of device, effect of scaling down devices on the device characteristics. And next thing is we have to cover the ITRS roadmap. The students should be aware that in the next 10-20 years what kind of device dimensions they are going to use for their circuit design. And the model issue, sometimes I've seen students don't use the device models efficiently because they don't know most of the parameters. Like typically if you take a Taiwan semiconductor process parameter, it's about 200 pages. And sometimes it is becoming more and more abstractness. We're trying to use a more abstract parameter rather than knowing its real validity. So therefore having a good knowledge of device modeling in the submicron dimension is extremely important. And SPICE model parameters, so like how this is related to the device characteristics and the device linkage and so on, that is also extremely important. And next aspect is the device degradation mechanism. Like when you go from one technology to next technology, how the device may degrade, like degradation, like due to hot carrier induced degradation. Like when you apply a voltage for a long time, the carriers might be injected from the silicon to from the channel to the oxide, changing its threshold voltage and so on. And as far as possible, we have to incorporate practical knowledge for students in the classroom. I thought it is extremely important. I myself went to a company, semiconductor company, 3 years as a visiting faculty, 1 day a week, and I learned why it is so important, because most of the textbooks are written on working devices, but when you go to industry, we come across devices which are not working, and textbooks never discuss about them in detail. So but you can get those knowledge by working in the industry for about 1 day a week, and then you can give more life to your teaching. And next topic, I think we have to consider is the bipolar junction transistor. Though most of the circuit use CMOS technology, still in certain places we use bipolar junction transistors. And when we graduate students, they should have a knowledge of what are BJTs and so on. And sometimes for high frequency circuits, we use HBTs, heterostructure bipolar transistors. And HBTs are basically silicon germanium composite device and so on. And silicon germanium, like what is silicon germanium? Like people know germanium, silicon, and when you make heterostructure with silicon germanium, what are the advantages and disadvantages for high frequency HBTs, heterostructure bipolar transistors? Then models for bipolar junction transistors. And sometimes what happens, we don't, if you go for a vertical BJT, this is basically vertical BJT, and if you want to go for lateral BJT in CMOS process, you should know the advantage and disadvantages of lateral BJT in terms of cost and performance, and that should be explained in detail. And in addition to that, we should be able to explain them the SPICE model parameters, and then self-heating effects. This is one of the serious problems we find in BJTs, especially for high frequency application. Self-heating problems, thermal effects, and so on, and how to efficiently take heat from the chips, microchips, and so on. So covering those topics is also extremely important. The next is the CMOS processing technology. So CMOS processing technology is, sometimes people think that processing is not it's a different area. It is expertise where only processing people should know about it, but designers may not be aware of it and so on. But in order to reduce cost, power dissipation, to improve performance, we should have exposure to CMOS technology. So designers should have the knowledge of physical implementation of circuits. So introduction to CMOS processes such as oxidation, diffusion, photolithography, etching, metallization, chemical mechanical polishing, all those things, they should be aware of it. In addition to it, how you integrate different processes to microchip so that it is used for the design of microchips is important. And another important aspect which we are not much aware in the academic world is the optimum cost. So students should be, we should make them aware of cost versus performance. Like, how can, chip communication technology is one of the very, very cost sensitive area. It's very difficult to predict cost of a chip also. Sometimes when people think that they can sell a product for $2, but by the time they design, the cost goes down to 50 cents, and when the manufacture it becomes 25 cents, but still you have to survive. So therefore, optimizing the cost of performance is extremely important. Layout to design rules, design rule checkers, checking, circuit extraction, and manufacturing issues like a given process. What are the manufacturing issues? Like, for example, you take an example, a threshold voltage. Most of the textbooks they write only one single threshold voltage for a MOSFET. But when you go to real life, we have so many threshold voltage for different devices, whether depending on the channel length or channel width. The threshold voltage depends on the dimension of the device also. So therefore, in addition to that, the threshold voltage may change over across a wafer. There is a distribution, and then students should know what is 2 sigma, 3 sigma simulation, 4 sigma, 5 sigma, 6 sigma. So as the sigma increases, what is that importance in manufacturing and so on. So those things are manufacturing issues should dust when we teach them the microelectronic circuit design. Assignment on layout on simple CMOS circuits is a good exercise, and then putting them in the real environment it also makes them more matured. Extracting active and passive components in a given process for design requirements. As I told you, we don't get in a chip technology, everything has to be implemented within the process given in the manufacturer. So obtaining active components such as inductors, capacitors, resistors, and so on in a given process is extremely important. So therefore, that is one that is also important. So that has to be considered. So next, the design topics to be covered as the delay. So delay is one of the important issue in circuit design. Usually the chips always fail due to timing issues. I always joke my students, timing is important in life because sometimes, when they graduate, if the market is good, it is easy for them to find employment. Whereas if the market is not that good, sometimes, of course, due to bad luck or something, they will be in trouble when they graduate. So therefore, timing becomes extremely important. Same thing the chip also. We tell them the clock and the data, they have to arrive at the right time. Then only you can make the chip work efficiently. The next thing is the power dissipation. Power dissipation, again, the static power, dynamic power. So all these kinds are becoming extremely important. Delay optimization. So all those things have to be covered. Interconnect issues, resistance, capacitance, minimizing interconnect delay, crosstalk, high-speed interconnects, on-chip decoupling capacitances, differential voltage signaling. So every issue in a chip design, it has is an impact on the performance of the circuit. And next thing is the combination circuit design. So various combination logic families such as static and dynamic CMOS, silicon on insulator, and subthreshold circuit design, dynamic threshold voltage design, sequence, and then we go to sequence circuit design, sequencing static circuits, flip-flops, latches, and things like that. So next I will take an example like a memory design. Memory in olden days, memory was a separate product, but nowadays memory is an integral part of a chip. We have variety of memories like dynamic RAMs, we have static RAMs, we have flash, and every chip has different blocks of this memories associated with it. So in case of design of non-volatile memories, DRAMs. So like what is the typical DRAM cell look? For example, we started with the DRAM with the 5 cell per transistors, and now the final architecture is 1 transistors for 1 cell. When we teach a topic, I think it's better to highlight some of the research aspect of it also, so that it gives them a scope for thinking for future. So in case of this DRAM, we have this bit line, word line, storage capacitor, and our job is to make these things as small as possible for the future. So next, and then but the capacitor missing. As the capacitor memory increases, the bit line capacitance will increase, and then this storage capacitor also larger, so that we have enough signal to noise ratio. So, and therefore we have to cover various of issues associated with the design of the memory cell, then designing these decoders, and then sense amplifiers, memory cells, efficient circuitry, I/O input-output design, and so on. And the device size is going on decreasing memory. Memory is, you can see the memory capacity is increasing every year. So knowledge of ITRS is extremely important, and they should have effect of scaling on MOSFET for performance. Power supply scaling, like power supply, is going on decreasing every year. How it impacts the circuit design and its characteristics. The leakage issues, as I told you, in a DRAM, the leakage becomes an important factor in determining the reflex clock rate. Higher the reflex clock rate, it increases the power dissipation in the chip. There are so many interrelating parameters, and our job is to give the student the right knowledge, so that we come up with we develop an well-rounded engineer, a microelectronic design engineer. Next, threshold voltage. Like we use different threshold voltage for memory, different threshold voltage for logic. So therefore, we have to highlight the effect of the threshold voltage also. Reducing the size of storage capacitors, because storage capacitor takes a lot of area in the chip. How can you make this capacitor dimension as small as possible? So we may introduce, high-K materials, like high dielectric constant materials, to reduce the size of the capacitors, so that when the newer process is offered from fabless companies, they can use it effectively in their chip design. And the noise margins in the memory cell, and sometimes they should have an idea of electromagnetic simulation because of the cross-coupling effect coming into picture when you keep the interconnects very close. So next important, that's all about, I talked about DRAM as an example for volatile memory. The next thing is the non-volatile memory. In a non-volatile memory, I think the flash memory is one of the very important memories, because flash is basically a dual gate device. It has a metal oxide, then we have a floating gate, then we have a thick oxide, and then we have a control gate. So when we incorporate electrons into the control gate by hot carriers, then they get stuck in the tunnel gate, and then the threshold voltage goes up. So this device master voltage, depending on the presence of, this is called a floating gate, we call this a control gate, depending on the presence of electrons in the control gate, floating gate. So you may have a low threshold or high threshold voltages. So these two threshold voltage corresponds to the states of the memory in the memory cell. And flash memory is mostly used in microelectronics for non-volatile storage. You can see the thumb drive has gigabit of flash memories. Or you can see nowadays even the laptops they don't have magnetic disk drives, they have flash memories. So it is one of the widely used memories. And then all the ASIC chips nowadays we put flash memory for variety of storage applications. And then so we have to highlight in the voltage. And next thing is we need high voltages to from silicon to floating gate, and therefore they need charge pumps to design on chip to DC to DC converter. Like people think that we use still 1.8 volts outside the chip, but we have to step it up to like 18 to 20 volts to write the memory, and it is important to give the concept of charge pump for students. And then next thing is we should always tell them what are the limitations of flash memory and how we can and when it can hit a dead end, and where are the scope for improving the technology, because as an educator we can't give them a knowledge where their knowledge stops thinking, stops. So we have to keep them continuous thinking process, give them continuous process so that they can come up with a good products for the future. So main problem of the flash memory is slow writing speed. So then are there any memory technologies where we can improve the writing speed for non-volatile storage? That is very important. So next memory is the ferroelectric memory, which can overcome the limitations of flash memory. The flash memory problem is, of course, you can have very high density memory. The problem is the slow writing speed and then limited endurance. So you can write only about 10,000 cycles in a flash memory. So but now people are working on new memories like ferroelectric memories, where we use material ferroelectrics to store memory state in terms of ferroelectric polarization. Since we are the originators of this technology, so we want to talk something about. I want to talk about something about this memory. There are only two non-volatile memory technology chips you can buy in the market. One is flash, another is ferroelectric. So in case of ferroelectric memories, basically they are capacitors. So you apply voltage, the material will polarize. Either this is positive, this is negative, or this may be negative or positive. So if you study the polarization versus electric field for these memories, they show a non-linear behavior. Ferroelectric field, the polarization and increases, and then it saturates, and when you bring the voltage back to zero, the polarization does not go to zero. You have some polarization left here, and then bring the polarization to zero, you have to apply negative electric field, and then at this point, you can have zero electric field, you can have opposite polarization, and therefore these two states correspond to states of memory. These memories are much faster to write, unlike flash, and they are unlimited endurance. You can write about 10 to the 12 cycles. They are radiation hard, and now there are already technology available to in the silicon technology, and companies like Texas Instruments, Ramtron, and IBM, they are already working in this area of ferroelectric memory, and you can buy this product in the market. And this is typically a ferroelectric memory cell. So it's a single and anytime. And you can see the calculation versus applied voltage for a linear capacitor, one state, you may call it as zero. And then the coercive voltage, and anywhere between 1 to 3 volt. So therefore, this ferroelectric memory does not need a charge pump. So, charge pump means you have to develop voltages in the chip which can go up to 18 volts. And the memories can be, you can make it work within 3 volt itself. The only problem is some exotic materials, but now you can integrate them, and the next memory, and ITRS predicts this is the memory of the future for storage. And here you can see the typical switching current you are going to get in a ferroelectric memory. So we have like waveform spectrum to down pulses. So when there is up and down transition, you get a large. There is no up and down transition, then you get a switching current. This is a current due to the typical capacitor, where this is the current you are going to get the polarization. We get a large current due to the polarization, and we can use them for memory applications. So if you go through the ITRS roadmap, so that memory they call ferroelectric field transistor is the ultimate memory. This ferroelectric of the MOSFET itself. So we have a ferroelectric of the MOSFETs. And rather than we use a floating gate structure and a control gate, where here we use a and polarize it in two directions, up or down polarization, then the source and this way we have one transistor memory cell. It has a good scalability, and it is a ultimate non-volatile memory. But the problem I think is on the gate of the material, then you grow some oxide at the interface, and then there is a fundamental problem to solve. Once that problem is solved, this may replace the flash for many applications. So now, whenever you think of technology, it's a very competitive technology, because any new technology, if you want to develop, you have to that has to beat or should have a higher performance as well as lower cost compared to the existing memory technologies. In addition to that, we should be able to scale it for a few generations. So that is why sometimes people say that the ferroelectrics may not be the ultimate solution, because they're all basically capacitors. When you try to scale a capacitor, the capacitor size goes down, then its capacitor value also decreases. So when the capacitor value decreases, the signal to noise ratio will decrease. So therefore, people we may not like to pursue capacitor-based memories for the future. Whereas if you use a resistor-based memory, resistors smaller you make, its value goes up. So therefore, any resistor-based memory will have a better chance of survival for scaling down for future. As I told you, these are all very capital-intensive technologies. Typically, if you want to open a fabrication facility may cost billions of dollars. So when you invest that kind of money, and you have to see how many generations you can use that technology. So performance, cost, size, and speed, and possibility of combining memory and logic. So can use the same aspect for memory and logic. That is another interesting aspect. Ferroelectric can offer that. Resistor-based memory is still not very clear. Energy efficiency, like how much energy you need to switch. So that is important, and we should have that energy efficiency. And next thing is the on or off ratio. That means, how much, what is the on-off ratio, like when you have, depending on the presence or absence of memory, how much signal to noise ratio we can get. And we want this signal to noise ratio as high as possible. So whenever you want to think of new technologies, you have to keep all these things in mind before we jump into that. Next thing is operation reliability. The ability of the memory and logic devices to operate reliably within their operational error tolerance, even in their performance specifications. That is also extremely important. Reliably, can you stay, because memory is memory. When you store 1, it becomes 0, then the main purpose is not satisfied. So 1 has to be always 1, 0 has to be always 0. Next thing is the operational temperature. Like typically, when you store a memory, you should be able to store it between -40 to 80 degrees centigrade for about 10 years. So any technology should offer that capability. CMOS technology compatibility. Can you integrate it in CMOS? That is also an extremely important aspect. CMOS architectural compatibility. Can it fit with the CMOS architecture? And so therefore, we feel, nowadays people are working on resistive memories like phase transition memories, maybe chalconite based or oxide based, and we hope that may have a big future over the time in the future if it proves if it proves its capability. So the next important topic I think we have to teach is the design of chip input outputs, ESD protection. VDD ground, digital input output, bidirectional pads and analog pad, noise issues, and I feel ESD is one of the serious problems to be tackled to get high yield in large volume products. When I used to consult in a company for about 3 years, I found electrostatic discharge is one of the important failures, especially when large volume products are involved. We have to assure their ESD compliance. So typically, as per the human body model, it has to withstand 2 kilovolt. So therefore, we have to come up with innovative ESD protection circuits so that even when our technology gets downscaled, the ESD circuit can take care of all the electrostatic issues. And then in the analog IC design, I think device modeling of analog circuits is important, analog component characteristics in a given process, and then device matching issues, because it is not a device matching is not like does not follow system-wide equations. You can't say the math doesn't work there. So you have to match identical size, shape, all those things are important. Frequency response, then noise effect, design of op-amps, frequency compensation, advanced current mirrors and op-amps, and comparators, band gap references, and we use basically textbook we use analog circuit design by Martin, or sometimes we use Allen and Holberg's book, and this is basically a first year or senior or first year graduate course. And in terms of, for RF circuit design, we teach RF MOSFET device characteristics, on-chip inductor characteristics and models, matching networks, wideband amplifier, tuned amplifier design techniques, low noise amplifier design techniques, RF power amplifier techniques, RF oscillator design techniques, phase locked loops, and frequency synthesis and things like that. And in the tools class, it's basically like a software class where software-based design, review of combination and sequential logic design, modeling and verification with hardware description languages, introduction to synthesis with HDLs, programmable logic devices, state machines, data path controllers, timing analysis, fault simulation, and things like that. Then this is an important class, electromagnetic effects integrated circuits, which incorporates even the packaging issues also. We discussed the interconnect design, not only the chip, in the printed circuit boards also, ideal and non-ideal transmission lines, crosstalk, non-ideal interconnect issues, modeling interconnectors, packages, and vias, non-ideal return paths, simultaneous switching noise and power delivery, power modeling, radiated emissions compliance, and system issues, high-speed measurement techniques, like whenever problems and so on, how to find the problem using time domain reflectometry and so on, and some of the electromagnetic simulator like ANSOFT, advanced design tools from Agilent and things like that. So overall, I feel what is the core sequence to introduce undergraduates and graduates in their micro design. So this is the course we follow in our school. So we start with the robotics, and then we go to the logic circuits, then we teach signals and systems, and then circuits and systems, electronics. This is the first year class, second year class, the third year class, and physical electronics, we learn semiconductors. And in the senior graduate, we have CMOS circuit design, we have computer architecture, semiconductor devices, digital design tools, analog IC design, RF CMOS circuit design, VLSI processing, formulation, mixed signal design, digital signal processing, electromagnetic in ICs, and design of power electronic circuits and power. So this is the curriculum. Though we are a small school, and then we have we try to give them pretty wide knowledge so that they will be successful when they go to industry. We also cover the rapid prototyping, the FPGAs also, so that for rapid, some companies use a lot about FPGAs, and they will get a good training when they go out. So next thing is so overall summary-wise, providing an well-rounded microelectronic design curriculum for students with limited sources is really a challenge. Ours is a small department with 12 to 14 faculty, but we could give the students well-rounded knowledge. As I showed you, the list of classes the students take, which can make them a very good designer, because they have a good background in physical electronics side, the digital side, analog side, RF side, as well as in tool side also. Tools are important. Most design we use the tools. And then microelectronic circuit designer should have a background in device physics, processing technology, circuit architecture, and design automation tools. And he should have the knowledge of analog, digital, mixed signal, RF circuit design, and packaging techniques. So I hope our curriculum covers all these aspects. And if you guys are interested, I can share with you guys, how to develop those curriculum and its impact and so on. Thanks a lot. Please, if you have any questions, please let me know. Hello?
Yes, sir. No questions yet. We're waiting. Anybody with questions can type them out in the chat window. Sir, one question is, how do you simulate and find out interconnection delay in capacitor and resistor in CMOS?
Yeah, we have, you can use SPICE simulation, but that is, we have this timing analysis also. Basically we extract, its capacitance, resistance, and all those things, and then we see whether we can put it, repeaters and things like that. So basically, you can do it in a, if you want to do in a system-wise, system where you can use timing analysis tools, or sometimes you can use SPICE also. But SPICE is time-consuming. Okay.
The next one, is there any common criteria for mixed signal design?
Mixed signal design, it depends on the chip you are going to design. Mixed signal design is a pretty general term actually. When some people put a data converter block in a digital circuit, they call it a mixed signal chip actually. It's a broad term. It depends on particular application.
Waiting for. Okay. So how do you calculate the assessing speed memory?
Usually we identify critical paths actually. A critical path, and then we do the simulation for the critical path and find out how much time it takes and all those things. And then if certain paths are giving more delay, then we go back and optimize that. So we do this critical path analysis.
Okay, sir. What is ITRS?
That is international roadmap for semiconductors. It is a www.itrs.net. So they predict how the technology is going to scale down for the future, and they follow that path actually. So therefore, you can be prepared like how the models are going to change, how the technology is going to change, and things like that. We always explain students that how the technology may scale in the next 10 years or 15 years and so on.
Okay, sir.
And it is available everywhere. You can access it and then you go through it.
Okay, sir.
It's just like a Moore's law. Sorry.
What is the difference between faulty analyzer and test analyzer engineer?
Test analyze engineer and fault, so I can say that, fault detection, like in the design stage, they do the fault detection and all those things, like they do simulation and find out the, faults and all those things. Whereas sometimes the test guy, when the chip wafer comes back, he developed the, test software, how efficiently he can test it. And the reducing the testing time is, extremely important. So, he has to come up with the software where, like, I don't know, when I used to go for a consulting company, like if it takes like 2 minutes to test, the manager used to become very upset because he says, it is going to take too much time and, find out where you can reduce the test time and all those things. So we will work on, making the, test time as short as possible.
Okay, sir. What is mixed signal track width in RF PCB design?
Oh yeah, in RF PCB design, we started that class recently. Like what happens was, people can design a chip, very high speed inside the chip. So once they take the chip, like put the package and then put in the PCB, the, speed goes down actually. So that is why then we thought, we teach them complete model, like they can make a model for a package also. Like we usually use the Ansoff tools actually, where from the chip pad, then it will go to like solder ball to a package. If they use package, or directly they use printed circuit board also. So then every step you have to incorporate the inductance, capacitance, and resistance, and then you have to see how the signal looks from the output driver to the point of interest. So, and this is extremely important. Otherwise, we don't have digital signals in a chip. We have basically analog signals, and then we have to make out how to identify 0 to 1, or we call eye diagram, how to make the eye opening as high as possible, wide-eyed opening. So that is why the electromagnetic concept in a chip or in a package or in a printed circuit board is extremely important. Especially if you see that when you go cross over 5 gigahertz.
Okay, sir. That seemed to be all the questions, sir.
Yeah.
If
and, send me email if any, I can give you like the syllabus of the class we teach and all those things. And since we have, a lot of industries in the town, we get a lot of students who always ask a lot of questions like, what can I do in the work and all those things, and it gives them, good motivation to keep our knowledge refreshed and things like that.
okay, sir. And the recording will also be available on iocee.org, sir.
Yeah, thanks a lot.
Thank you, Dr. Kalkur.
Yeah, thank you. Bye. Good night.
Right.